You know, every single time someone pulls out their phone and opens Uber, Swiggy, Tinder, or Google Maps, a massive, globally distributed system instantly kicks into gear. And it does all this to answer what seems like a really simple question in well under a second. Well, today, we're diving deep into this explainer to unpack the actual geospatial architecture that solves real-time location matching at planet scale. We are literally going from first principles all the way up to a production-grade high-level design, the kind that handles millions of queries with sub-200 millisecond latency.
Okay, so it really all boils down to this. Given my exact location, who or what is within K kilometers of me right now? That right there is the core geo-proximity problem. Now, I know it looks completely trivial on the surface, but think about the scale. When you have millions of active drivers pinging their GPS coordinates every 4 seconds, and millions of riders simultaneously opening the app to find a ride, answering this question millions of times a second becomes an absolutely incredible engineering feat.
So here's our roadmap for the explainer. We're going to start with the core problem, learn how to flatten our 2D world into a 1D line using geohashes, build out an Uber-style architecture, tackle the harsh reality of latency and hot shards, and finally wrap up with the trade-offs and observability metrics you need to keep it all running.
All right, Section 1, the geo-proximity problem and exactly why naive approaches completely break down at scale. Let's get into the mechanics of why brute force is a terrible idea here. A classic staff engineer reflex is to take really hard multidimensional problems and project them into easier single dimensions. Because if you just write a brute force SQL query, literally iterating through every single driver in your database schema to compute their haversine distance to the writer, that is an ON operation. At horizontal scale, doing that will just burn your system to the ground. Even if you try sorting by X and Y axes and doing bounding box binary searches, it's still way too inefficient. The secret isn't asking everyone where they are, it's building a spatial index. You want a data structure that inherently just knows who is near whom.
To use highly optimized standard databases, we need a mental model that converts our 2D coordinates into 1D data. Enter the concept of space-filling curves. Imagine a mathematical function, something like the Hilbert curve, that basically snakes its way through a 2D map, flattening the whole thing out into a single 1D ribbon. The absolute magic here is locality preservation. 2 points that are physically close to each other in the real world will generally stay close together on this 1D ribbon. This is a total game changer because it unlocks our ability to use standard B-trees, sorted sets, and basic string lookups for complex spatial queries.
Moving on to Section 2, Geohash 2D to 1D, interleaving bits for fast proximity search. Let's see how this brilliant concept actually powers the workhorse algorithm of modern location matching.
Think of a quad tree, continuously dividing a map into 4 smaller squares. Well, Geohash basically encodes this mathematically. Step 1, we have the latitude range and emit a 0 or a 1 depending on which half the point falls into. Step 2, we do the exact same thing for the longitude. Then we just interleave those latitude and longitude bits together. Finally, we take those groups of 5 bits and encode them into a base 32 string. Boom! By following these exact mechanics, a really heavy 2D circular query magically transforms into a highly optimized 1D string prefix search. If 2 geohashes share a long prefix, like TDR1V, they are sitting in the exact same bounding box. Finding nearby drivers literally just becomes a simple database string matching exercise. How cool is that?
But hold on, because there is a catch. Geohashes can lie to you. We call this the boundary problem. Imagine one point is just slightly east of the prime meridian, and another is just west. They might literally be 10 meters apart in the real world, but they end up with completely different geohash prefixes simply because they straddle a major binary subdivision line. Because of this little quirk, your query logic must always check the target cell plus its 8 surrounding neighboring cells to guarantee you don't miss a nearby driver. If you skip this step, your system will fail silently and your users are just going to stare at a completely empty map.
Now, while Geohash is definitely the industry standard, the really advanced production systems have actually moved over to H3. H3 was developed and open-sourced by Uber, and it uses hexagonal grids instead of squares. And you might be wondering, why hexagons? Well, a hexagon has exactly 6 neighbors, and every single one of them is the exact same distance from the center. Squares, on the other hand, have edge neighbors and corner neighbors, which introduces annoying geometric distortion when you're trying to do perfect radius queries. H3 elegantly fixes those geometric constraints, giving you incredibly precise mapping for things like city-scale analytics and dynamic surge pricing.
All right, Section 3, the Uber-style architecture. Ingest, match, and shard. Now that we have the algorithms and concepts down, let's architect the high-level design and see where this data physically lives. In the real world, you rarely build a spatial engine from scratch. You just leverage an existing database. If you're building something like Yelp or Airbnb, where text search and complex aggregations are super important, Elasticsearch is fantastic. If you're dealing with complex polygons and need full SQL support, PostGIS is your go-to. But for real-time mobility systems where a driver's location changes every few seconds, Redis wins outright. No contest. Its in-memory sub-millisecond latency, combined with native commands like Geosearch, makes it the ultimate engine for this specific workload.
So, to build a true Uber-style architecture, we have to deliberately decouple our services. We set up a massively write-heavy location ingest service. Its only job is to track driver heartbeats coming in every 4 seconds, and it writes those exclusively to Redis masters. Then, completely separated from that, we have a read-heavy matching service. This handles the rider's requests by reading exclusively from Redis replicas. Splitting the architecture like this is absolutely crucial. It ensures that a huge spike in driver location updates, say 50,000 drivers leaving a stadium at once, doesn't consume all your resources and crash the matching latency for riders trying to get home. They scale completely independently.
But there's a sneaky little bottleneck when reading from those replicas. Once you find the nearby drivers, you still have to filter them using business logic, right? Stuff like vehicle type, minimum rating, or accepted payment methods. If you pull 10,000 raw driver profiles across the network to your application server just to throw 9,900 of them away, that is a massive latency nightmare. So what's the fix? We push the compute to the replicas using eval-r. This is a command introduced in Redis 7.0 that lets you safely run read-only Lua scripts directly on the replicas. You do all that heavy filtering right where the data actually lives without any risk of accidentally writing data and corrupting your replication contract.
Section 4. Latency and hot shards. Surviving real-world scale. This is where textbook theory meets harsh operational reality. What actually happens when our database slows down or a megacity gets completely gridlocked? Listen. Tail latency is the absolute enemy of a good user experience. If a naive matching service fires one massive query and that database node is running slow, the writer is just left staring at a spinning wheel. The senior engineer playbook solves this with the scatter-gather pattern. We take our query and fan it out in parallel across multiple shard subregions using Go routines. And here is the kicker. We strictly enforce an SLA timer. If a node is too slow, we use context cancellation, like CTX done in Go, to kill the operation, and we just return a partial response to the user. Why? Because in location matching, freshness beats completeness every single time. Showing a writer 8 nearby drivers in 100 milliseconds is infinitely better than showing them 10 drivers in 800 milliseconds, because in 800 milliseconds those drivers have already moved.
Next, we need to talk about data partitioning or sharding. If you use standard native hash sharding, Redis is just going to mix up locations randomly across your cluster. But think about it, geography is highly correlated with time. At 5 p.m. on a Friday during a rainstorm in Manhattan, that single shard is going to completely melt down, while a shard hosting a sleepy town in another time zone is doing literally nothing. Geography requires human-aware, city-based sharding. By manually pairing a crazy dense megacity with a sparse off-peak region on the exact same masternode, you perfectly balance the CPU load across the entire 24-hour cycle. It's a brilliant operational fix.
Which brings us to our final section, Part 5. Trade-offs and observability, the senior engineer's playbook. Let's synthesize the core metrics and the really tough decisions that make a system like this bulletproof in production.
Anytime you design a distributed system, you slam right into the trade-off triangle. You have to choose what you're willing to sacrifice. For geoproximity matching, we very intentionally throw strong consistency out the window in favor of high availability and ultra-low latency. Think about it. A driver's location is ephemeral, soft state. They're moving every 4 seconds anyway. If our read replica is 200 milliseconds stale, who cares? That's completely fine. But if the system goes down or latency spikes, users can't get a ride and revenue literally stops. We optimize the entire architecture for speed and availability above all else.
But how do you actually know if it's working properly? Well, a system you cannot observe is a system you do not operate. You have to instrument everything. You need to track the red metrics, rate, errors, and duration, and break them down to the specific city shard. You want hard alerts firing if your partial response rate jumps above 5%. And critically, because remember those Geohash boundary issues we talked about that fail silently, you need to deploy a shadow ground truth job. This is a separate process that constantly samples weird queries, runs that heavy brute force Haversing math in the background, and immediately alerts you if your highly optimized system is somehow missing nearby drivers.
I want to leave you with this final, absolutely vital staff engineer thought. A correct algorithm that you cannot observe, shard, or roll back is not a production system. We spent a lot of time on geohashes and space-filling curves in this explainer, but the true engineering happens when you take that pristine algorithm and force it to survive the absolute chaos of the real world. So my question to you is this. The next time you open an app and it instantly knows exactly what's around you, are you just going to see the map, or are you going to see the interleaved bits, the Lewis scripts, and the hexagonal grids quietly doing all the heavy lifting? Keep learning, keep building, and I will see you in the next explainer.